2020 scholarship exam, question 3. Right, collisions. You've got massive neutron and one electric volt. Slider S1 is moving along an air track at constant velocity and collides elastically with the stationary identical slider S2 as shown on the diagram. Explain why S1 stops and S2 moves off with velocity v. So their masses are identical, and it's completely elastic collision. So we can say that both momentum and energy conserved, conserved. Cool. What else have we got? So energy. So this whole, if you look at this question, I guarantee it continues on. This is a mechanical impedance question. Impedance is when you have things colliding and one will bounce off and the collision is completely elastic. So first we're going to say that we'll write the conservation momentum. So M1 V1. And it's just M because all the masses are identical. So it's going to be equal to mv final 1 plus mv final 2, and we're going to have the energy consideration half mv1 squared, or v initial squared I should say, is equal to half mv final 1 squared plus half mv final 2 squared. And in other words, we have v1, so I'll just divide everything by m, and for the energy formula I'll times by 2. So we're going to have v1 is equal to vf 1 plus vf2, and we're going to have v and vi squared is equal to vf1 squared plus vf2 squared. However, vi is equal to vf1 plus vf2, so I want to substitute this, or this here, into here. So that is equal to bracket vf1 plus vf2 bracket squared, which is equal to, this is just expansion of quadratic equations. So we get vf1 squared plus 2 vf1 vf2 plus vf2 squared. Right, so this, I'll just pause and write out like a short answer. Right, so I said this is only true if either vf1 or vf2 is 0, because you can see we've got vf squared, vf1 squared plus vf2 squared equals vf1 squared plus 2 vf1 vf2 plus vf2 squared. So one of these has to be 0, so it makes this term 0, so it makes that term 0, so then you just get vf1 is equal to vf1 final squared, or if vf final squared, and yeah, so one of them has to be 0 for this statement to be true. The only thing I couldn't quite, I looked up, I've done it, these questions are quite common, actually very common. This is only true if, so thus vf1 is 0 as a collision occurred. I'm not entirely sure about it. I can't think of a physical reason why this wouldn't stop and this wouldn't continue away. But the math doesn't show that it's impossible, just that one of them has to be 0. But anyway, I could spend ages on that. Right, in a second experiment, slider S1 is given a velocity of 1 meters per second. That's going to be handy along the air track and collides elastically with another slider S3 that has a mass n times that of S1 and is stationary. So in other words, we've got M3 is equal to n M1. It's like a amount. So n times m1 would give you m3. Is that totally true? Yes, it is. Right, so show that after the collision, the velocity of S1 is given by this formula, and the velocity of S3 is given by this formula. Just a caveat, I've already done this question. I usually do the scholarship questions before I do the videos. This question was hideously tricky, and the fact that I got lots and lots and lots of different ways to show that V3 equals some variation of this, not exactly this, and V1 equals some variation of this, but not exactly this. Different forms, but still the same. Or yeah, just rearranged differently, with different brackets and so on and so forth. You'd need to use the back page of one of these, the back page of like your exam to try and do all the working for this. Unless you've already practiced this question before, which you might have because it's a common question. I'll chuck in the video description the derivations of like the generic forms of these. I think I'll leave out the Wikipedia version. If you look up mechanical impedance on Wikipedia, it comes up with the horrendously more complicated version of these. Anyway, I better get going. Energy conservation. Energy conservation. Conservation. What do we got? So that is going to be equal to, we've got half M1, it should be a 1, V squared, because we're coming in with V, and that's just going to be 1, so we'll get to this soon. And that is equal to half M1, what do we got, half V1, and this is going to be V1, that V1 up there, V1 squared, plus half, okay, we'll just go M3 for now, but we'll substitute that out soon. M3 V3 squared. And in my work, I just had like a wee star. M3 is equal to N M1, but I put that up there because that's what I figured out from up here. Right, next line, momentum conservation. Momentum conservation. And you're probably wondering why I'm using momentum and energy. This is the way you solve a lot of these mechanical problems. If it's elastic, you combine momentum and energy conservations into like one formula, and then you can extract a whole lot of information out of there. So we've got the initial momentum, m1v, and that's going to be equal to m1v1 plus m2v2, m3, because we're dealing with, that's going to be v3. I just realized I made a typo. Or m1v is equal to m1v1 plus n m1v3, v3. Haha. Now we can say thus v, because that's just v here, and we're going to divide out all the masses, so we're going to have v1 plus n v3, and that is just equal to 1, because v, the initial velocity, is 1 meters per second, which is going to make things a bit easier. And then the energy formulation will just divide, we'll just do the same thing. We have v squared is equal to v1. This is just the energy. I've times everything by a half, and then I've divided everything by m1, and I did the trick where I did here to the energy as well. So I've swapped out m3 for n m1. So we get v1 squared plus n v3 squared. And that is also equal to 1, because v squared, or v is just 1, so 1 squared is 1. Cool. Right, what did I do next? So we have 1 minus v1 squared, just this energy consideration, is equal to n v3. Now this is where you start getting diabolical. That is equal to, we factorize or unfactorize, put this into brackets, 1 plus v1. This is a step that I didn't think of, that I did things differently the first time round, and then I was like, there's got to be a more elegant way to do this. which there was. So you factorize this out, and you get the 1 plus V1 times 1 minus V1, which is the same as this here, and that equals NV3 squared. Except for, however, we have, I'll just check, however, what do we got? 1 minus V1 is equal to NV3. And this is the momentum consideration. So we've done the energy consideration. Now we're going to substitute in the momentum. So you've got to take the energy, you've got to like derive a formula for energy, and you've got to put the momentum into that formula. So you can't just rearrange the energy twice and substitute the same thing back in. Otherwise, you just go around in circles. So what do we got? 1 minus V1 equals NV3. So I can swap that in for here. So I have 1 plus V1. But instead of having 1 minus V1, I'm going to have NV3. Yeah, totally am. NV3 bracket, and that equals NV3 squared. In other words, we can cancel out the n's, divide both sides by n, divide both sides by V3. So we get V3 is equal to 1 plus V1 plus 1. Except for, so sweet. Right, now we've got V3 related to V1 and I don't know, some other, just 1. We're going to use this formula here. We're going to rearrange this for V3, equate the two together so we can cancel out the V3 and have V1 with relation to the n and the other numbers. So we know that this is also equal to, move the V3, well, hold on, I'll move the V1 onto this side, so it'd be 1 minus V1 divided by n. And that's just this one here rearranged for V3. So in other words, we have, what have we got? How much space have I got? Not much, I'm going to have to use this line here. So we've got, so V1 plus 1 minus 1 minus, what do we got? V1 bracket over n is equal to 0. And we'll times everything out by n. In other words, we've got n V1 plus n minus 1 plus V1 equals 0. So we have, and that equals, I'm going to pull the V1 out. So we're going to have V1 n plus 1 plus n plus 1. Because we had that, there's that positive n, where's the positive 1? Is there a positive 1? Hold up. No, it should be minus 1. Cross that out. That should be minus 1 because that's that minus 1 right there. And now we can say that we'll move this to the other side and then we divide by, so move this to the far side and that'll be minus n plus 1. Yep, it totally will. So we're going to have, we'll do this over here. I'll have to run out of space. I'll do it down here. V1 is equal to, bracket, so it would have been, move the negative 1 to the other side, so it's going to be 1. And then there was positive n, so it's going to be the other side, it's going to be negative n. And then we divide by n plus 1. N plus 1. There we go, and we got the first one up here. Cool, what else we got? And V3 is equal to V1 plus 1. So it's going to be 1 minus n over n plus 1 plus 1. But another way to write that is literally to write 1 minus n over n plus 1 plus n plus 1 over n plus 1. I use the same denominator. That way I can just add these two together. And this is the diabolical trick, doing this. Going from 1 to n plus 1 over n plus 1. And that is going to equal to, we're going to get same denominator. So we're going to have v3 is equal to, how many? We're going to have 2. And we're going to have minus n plus n, which equals 0, over n plus 1. So we got v3 equals 2 over n plus 1, and v1 equals 1 minus n, and then over n plus 1. This is like it is quite a diabolical question. All the steps that I did, if you did this by yourself, you'd have to go around quite a few circles to get there, but you get there eventually. Yeah, this is going to be a long video. Right. And the third, we can see that. In the third experiment, two sliders change roles. So the S3 is moving at a velocity of 1 meters per second along the track and collides elastically with S1, which is initially stationary. Use the answer from AII, noting that S1 has a mass of n, or 1 over n times of S3. Show that after the collision, that and that are true. So, from before, this is going to be like a 30-minute video. From before, we have V1 is equal to 1 minus n over 1 plus n, and V3 is equal to 2 over 1 plus n. So instead of having n, we're going to have 1 over n. So we're going to swap n for 1 over n. Cool. So we're going to have, I'll do it down here, V1 is equal to 1 minus 1 over n over 1 plus 1 over n. And to get rid of the 1 over n, so we're going to times by 1, but we're going to times by n over n. And that is going to be equal to, the top, we'll do the top line first. It's going to be n, so n times 1 is just n, and n times 1 over n is just minus 1. And then we're going to have n again plus 1. And you'll notice, haha, we've got the first one. This is V3. And then we're going to do, and V3. This is like the clever trick, doing these times like n over n and the previous page. That's like a very rare but quite often somewhat common trick you have to use for scholarship physics. Not always, but 2n. Oh, hold on. No, 2 over 1 plus n. 1 plus 1 over n, because we're substituting it out. And we're going to times this by n over n. That is going to give me 2n over n plus 1. The only thing is, we have S3 is moving, but S1 is stationary. And thankfully it's moving at 1 meters per second. Otherwise, the previous algebra that we did over the page relied on the fact that this equation is set to 1, and this equation, wherever it is also set to 1, the momentum equation. So if this wasn't set to 1, we'd have to go back to square one and go rearranging again. Or we could just scale it up with the velocity. So you get to the end and then you'd scale your final answer. Because these functions here just give a ratio of velocities. So if you have a collision, it'll depending on the masses, it'll tell you the ratio of velocities those masses will have with respect to each other. Sweet. So I'll just pause it and then write out the last little bit. Right. So I've quickly said that, however, S3 is moving and S1 is stationary. So it's the reverse to the previous question. So V1 equals 2n over n plus 1, and V3 equals n minus 1. Divided by n plus 1. Right, so we've got use the result of 3 to show that if massive bat is swung with the top speed of v, to hit a stationary light ball in elastic collision. The top speed of the ball is approximately 2v. So this is very similar to a question like 2 or 3 years ago where you had a ball, I think it was like swinging around a rope and a baseball bat hit it, and you had to show that the velocity was going to be 2v. So I just quickly pause and write out like the top wee bit. Right, so I said the ball is originally stationary, so we use the stationary one. V1 is equal to 2n over n plus 1. I'll just try and keep that up at the top line. I'm going to leave out the meters per second because I can't be bothered. Scaling by v, so scaling. I mean, I had to check. Well, I did actually check the answers for this. This is just if you assume it's got 1 meters per second, 1 meter per second. But like I said before, these two here give a ratio of velocities compared to each other. So you can scale up by a velocity and it'll still give you a ratio between two velocities. So that's literally what I'm going to do. I'm going to scale up by v. So we're going to have v1 is equal to 2n and then over n plus 1, and then we'll just scale up by v over off to the side. I'll check a full stop here. When the differences in mass, in mass is large, n plus 1 is approximately equal to n. There we go. So yeah, when you've got a massive difference in mass, this n value becomes huge because that tells you the ratio of the different masses. So we have V1 is equal to essentially 2nv over n, which is just equal to 2v. Cool. Right, what are we in? 22 minutes in. God, this is going to be a long video. In the reactor of nuclear power stations, fast neutrons with energies of 2 mega electron volts typically are produced by fission of U-235. For a chain reaction to occur, these neutrons must be slowed down to energies of 1 electron volt or less by colliding with materials such as heavy water that contains hydrogen nuclei with an additional neutron. So this is just a proton, and this is deuterium or deuteron, I think it's called. Calculate the velocity lost when these fast neutrons are slowed down. So that's going to be fairly straightforward. You're going to calculate we'll calculate the kinetic energy beforehand, kinetic energy afterwards, and that should be it. So we're going to have the EK of the 2 mega electron volt one is going to be half mv squared, and that's going to be equal to, we know voltage is, the units are joules per coulomb, so we'll check a delta there for energy, just because it's going to get confusing if we don't. I'll just do little q for charge. So we can see that charge times voltage equals energy, so it equals QV. And that helps us go from electron volts straight to energy. In other words, the velocity is equal to square root 2QV over the mass of the neutron. I did do the working. The charge is 1.6 times 10 to the negative 19. The velocity, the voltage, I should say, is 2 times 10 to the 6, positive 6. The mass is the mass of the neutron, which is over the page. What do we got? 1.75 times 10 to the negative 27. I'm not going to do the working. I've already done it before, but because I'm running out of time. So we get 1.956 times 10 to the 7 meters per second negative 1. And then if you do this same equation, so this is for 2 MeV. For 1 EV, it's literally V is equal to, what did I get? 13,821. You literally just plug the same numbers in. Instead of voltage being 6 million, it's just 1. 0.89, I think I got 0.89 meters per second negative 1. So your change in velocity, delta V, is equal to this minus this. I'm just going to skip the working because I'm going way over time. 95461 times 10 to the 7. And that is equal to, round it up to, I'll do 4SF, 1.955 times 10 to the 7 meters per second, -1. Right. Cool. Using the results from A and B, explain why heavy water is used to slow down fast neutrons. Suggest the reason why heavy water is used rather than common water. So I sort of have known this for a while since teaching modern physics, but the way to figure this out is you'd have to have a lot of chemistry knowledge. Water is not just H2O binded together all the time. If you know about pH, you got hydroxide ions and you got H plus ions. The hydroxide ions we can forget about, but the H plus ions are just protons, and they are pretty similar mass to neutrons. If we know from the previous page, if a fast-moving neutron hits one of those protons, that proton will zoom off. The neutron would lose all its velocity, the proton would zoom off, and then you'd have like a colliding bang, 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 bang. But however, quite often the proton by itself would absorb one of those neutrons. You don't want that. So there's two things to consider: the impedance matching and the absorption. So if you tacked on another neutron to one of those protons, one of those H plus ions, then you wouldn't have to worry too much about the absorption. However, it would make the mass 2m, so the slowing down wouldn't be as much, but it's still, quite irrelevant, I should say. And when the neutrons they slow down until the whole system gets into thermal equilibrium. Right, so I'll pause and write the final bit of the answer. Right, so it said you want the moderator to have similar mass but not absorb a neutron. So H plus isotope, deuterium used in heavy water is ideal. And I've just note mass of the H plus isotope, so deuterium, is roughly equal to 2 neutrons. Just a side note, this is probably the hardest scholarship question that has been in one of these exams for quite a long time. Good question. I'll chuck in the video description a whole lot of videos that'll link to solving, or that'll give a lot more overview than what I've done here.